as was mentioned, I'm the Vice President Exploration with Kuya Silver Corp. Um, and we're operating one of the oldest mining districts in North America, in the Cobalt, Ontario silver camp. So this photograph here, okay, good. This photograph here is a drone photo of Kerr Lake, and Kerr Lake, it's one of the major silver producing camps or silver producing areas in Kerr Lake. And this, you can see here, there's a little bit of a sort of depression here, continues on down through here, about through here. And that's what's called the Carson vein. And that one produced almost 12 million ounces silver just on its own. And I mean, the Cobalt Camp, it's renowned for extremely high grade silver. And this is some of the mine workings here. This is what's called Crown Reserve. And right over here is another mine called Kerr Lake Mine. And I really want to emphasize right off the bat that this is a camp where inches matter. It's a very, very tiny camp compared to, say, somewhere like Kirkland Lake, where, kilometers are sort of what's being measured in cobalt. 100 meters is a long distance. So just our quick legal disclaimer here, more in just for completeness sake. So Kuya Silver, who are we? We're fairly new to the North American market. We've got an epithermal vein system, most likely porphyry related, in the central Andes of central Peru. And that's virtually all I'm going to talk about for our Peruvian project, except to say that we do have 13 million ounces defined in this in a maiden mineral resource, and we're expecting to go into production in that probably sometime in the next 6 months to a year. So this is our Silver Kings project up in Cobalt, Ontario. It stretches about 30 kilometers by approximately 10 kilometers right through the major heart of the cobalt mining camp. And one of the things that we're very proud of is that we've got 100% ownership of this property. It hosts approximately 1/6 of total silver production in the cobalt mining camp, which produced approximately 550 million ounces. So we've got documented about 96 million ounces. And they're primarily hosted in what are known as 5-element veins. And these 5 elements include silver, arsenic, cobalt, nickel, and bismuth. So there's 2 main areas that I'll be talking about here in a little bit. One is this area up in the north called Kerr Lake. And another one is to the south, termed Silver Setter. The Kerr Lake area produced about 60 million ounces silver on its own, and Silver Setter produced an additional 20 million ounces. And by the way, this is in addition to any cobalt. So I'm not talking silver equivalency. This is just silver. So who are we? This is our crew up in the Cobalt Camp. So here's me in a photograph taken in Greenland a couple of years ago. Ben Mark, who's sitting right here, is our project geologist. Photo of him in Colorado. And then missing are Sarah Buck and Katie Chahowie. They started working with us back a few months ago here when we started our drill program. A bit of background on me. I was the senior geologist with First Cobalt Corp. We had the property back in 2017, and I was involved from 2017 through to 2019. Did a lot of mapping through the project, and then Kuya Silver brought me back on. So this talk was originally set up as a talk at the Toronto Geological Discussion Group. So I wanted to bring in sort of the attention to Toronto, but I left it in here. And the reason I left it in here is the camp was sort of it was sort of discovered about 120 years ago. But at the time, Toronto was the major city in Ontario, and cobalt very, very quickly became the other major center of attention. So it was discovered in 1903 with production between about 1904 and 1989. The bulk of that production was definitely in the first sort of 20-year history in the camp, and it's tapered off ever since then. Like I said, it's produced on the order of 550 million ounces of silver. And just for a bit of relative math here, 550 million ounces at $25 per ounce is approximately 13 billion, almost $14 billion. It also produced very significant quantities of cobalt, despite the fact that cobalt wasn't in demand at that point, but about 26 million pounds, and about 2 million pounds worth of nickel as well. Now, with cobalt, you need to understand very clearly that this cap is extremely high grade. And I've seen grades recorded credibly up to about 18,000 ounce per ton. That corresponds at about 55% silver within some of these veins. So exceedingly rich veins, and that's one of the hallmarks of cobalt. Peak production was in about 1911. So the production rose very, very quickly. And then once the high grade was sort of developed, it tapered off and started to decline. Not a lot of people outside of cobalt know this, but it is the birthplace of Agnico Eagle. Agnico being AGNICO. And they do remain the largest or one of the larger landholders to this day, and they still hold the bulk of the major historic properties. But very, very importantly, from sort of the larger geological standpoint, prospectors that made their start in cobalt then branched out and discovered areas like the Timmins mining camp and the Kirkland Lake camp and the Rouyn-Noranda camps. So it was sort of the birthplace of hard rock mine in sort of Ontario and Quebec, both literally in terms of it was one of the first, but also figuratively in terms of, that people branched out from there. More just for interest, Thomas Edison had a nearby mine. He was looking for cobalt and had a mine in sort of in the general area. But at the time, with Toronto being sort of the major center that it was nowhere near as major as it is today, and it's got cobalt to thank for that in part, because it helped to launch Toronto as a premier international mining center from a financial standpoint and for credibility. Bay Street, Yonge Street, the Toronto stock market were largely built, at least in early days, on cobalt money. The first branch of the Canadian Imperial Bank of Commerce was in cobalt, with the head office being in Toronto. It was also the first area of the branch office of the Ontario Provincial Police. And for those that know Casa Loma, it was predominantly built on cobalt money. So cobalt itself, back in sort of the turn of the century, very, very modern town. It had things like electric tramways, aerial cable cars, sidewalks back when this was relatively unheard of. It also had a compressed air pipeline to the mines. The stock market in cobalt actually predates the one in Toronto. So again, very, very advanced town for its time. It had theaters, it had dance halls, you name it. I want to say it had, Ben, was it an opera or was it, there was other sort of
There was 3 theaters.
Theaters.
Opera house also.
Yeah, yeah. It was so important that Edward, Prince of Wales, did a royal visit in 1919. And our project actually, to back up a little bit, was actually named for the first hockey team, the professional hockey team, the Cobalt Silver Kings in cobalt. And just a bit of sort of background on it. It's both my boss with Kuya Silver and Frank Santaguida, who's the former VPX with First Cobalt Corp, are diehard hockey fans, and they wanted to name the new joint property after a hockey team. So that's where the project got its name. Okay, so like a lot of the mines, this camp was first discovered in the with the emplacement of the railways. But even backing up a little bit before then, the initial discovery was most likely made by the First Nations. And this is where things get a little bit complicated because technically the First Nations may have just found glacial drift as opposed to the silver veins themselves. But regardless, they knew that there was mineralization in the area. And these trinkets and stones were traded as far away as modern day Georgia. And this predates sort of colonization, I guess, if you want to call it that. And I'd like to do a call out to Matachewan First Nation, Temiskaming First Nation, Temagami First Nation, and to the Métis Nation. But it was then rediscovered by loggers when they were pushing the railway through. And this slide here, this is from North Bay through to Cochrane. This is back when English Canada was trying to assert dominance on the area. bring farmers, settlers, etc., into the area, and they tried to push the railway right through, right near the western boundary of Quebec. But it was largely just to get people in. So quite a few sort of larger than life tales as far as how cobalt was actually discovered. Sort of the classic tale is the story of Fred LaRose, who was a blacksmith, sort of in cobalt, take your pick, a hammer, an axe, whatever. And there was a fox that was apparently, bothering him. So he threw the axe and it hit a piece of rock and chipped off plate silver. And he realized there might be something to it. But one of the first sort of credible stories is in Silver Satyr, which is actually not even in the cobalt camp. It's the southern extent of it. It seems to have been discovered in 1902, 1903 with a prospector in there. He blazed a tree on top of a vein and then was having a hard time trying to find that, put together a map and sent off another buddy of his to go in and try and refine that area. They apparently didn't find it, but they did find the Keeley Frontier mine instead, so that's good consolation. But they later did find the blaze on the tree, apparently. So, take your pick as far as what you prefer to think. But once it was discovered, I need to emphasize just how quickly this town grew up from sort of a small frontier town into a fairly significant major city up in northern Ontario. So this photograph was taken in 1905, and it shows exactly how rugged and sort of frontier the area was. This is the train station in downtown Cobalt, which is still there, by the way. 2 years later, in 1907, you've now got how many more buildings that have been built in? Very, very ramshackle. City planning was absolutely at a bare minimum. And then 4 years after that, you've now got mills on the side of the hills. You've got hills stripped off, and this would be where the aerial tramway would be as well. So very, very, very rapid development. A few photographs of some of the early buildings in Cobalt. So this, as far as I'm aware, is called the Prospect Hotel. It burned down in a subsequent fire, but very, very good looking building by the standards of the day. This is in the nearby town of Haileybury, where there's an electric streetcar, tram car, and then paved sidewalks. I mean, it's they're wood timbered, but regardless, and ladies walking around. And there's actually stories about Haileybury because they're separated by about 4 kilometers, give or take. And the story was that the mine managers, they didn't want to live in Cobalt with the workers, so they moved to Haileybury and brought the money with them and developed things like Millionaires Row and major turn of the century mansions in Haileybury instead of Cobalt. But downtown Cobalt, here's the old stock exchange. Judging by the cars, I'd say about 1920s, give or take. So right before the Great Depression. Okay, but what's driving this is the silver and the cobalt high grade veins here. So here's an engineer, and this is actually at the Keeley mine in Silver Satyr, but it shows about a 10-inch wide vein here that was documented as being 12,000 ounce per ton silver. So just, yeah, I mean, with some of the discoveries we've made here, it's nowhere near as high, but 12,000 ounce per ton at about $25 per ton, that's $300,000 per ton of rock. So again, cobalt it's a very, very tight system, but there's very much good prizes to be had here. This photograph here shows bags of silver packed up in front of one of the mines for shipment. And this is a ton of solid silver bars at yet another mine called the Buffalo Mine. Here's an example of a nugget brought up from depth. So that'd be about 3,000 pounds, brought up in 1906. I don't know what the grade is, but I'd estimate on the order probably 30, 40, 50, 60% silver, something like that. This is the Carson vein here, and this is actually on Kuya Silver's Crown Reserve property at Kerr Lake. It was documented to be up to about 2.5 feet wide, and I think there's an axe handle in here somewhere for scale. Actually, that's probably it right there. But it was one of the richest veins, if not the richest vein in the entire camp. This section within Crown Reserve produced over 9 million ounces of silver over about 300 feet, and it averaged 217 ounce silver per square foot. Okay, so the town of Cobalt, and I mean this is some of the birthplace when the Ontario government really realized, and the Canadian government, that they had to start dealing with claim management and things like that. This map here shows the claim distribution sort of in the town of Cobalt, and the town of Cobalt would sit probably about within this area right here. But each one of these claims would have been either owned by a separate person or a consortium or a company or whatever the case is. Some of them were owned by several, and that's a mile for scale. Now, within this claim here, which is now what's called Nipissing Hill, this is a trench map showing the distribution of trenches within that same area. So from here to here is, I think, 200 meters, and you've got something like 200 trenches cross-cutting that hill. This is a photograph of what it looked like at the time. I mentioned the high pressure gas pipeline. That's the pipeline snaking its way across the property right there. And if you go to Cobalt, still see that it's a 12-inch cast iron pipe, and it's still there. But no in this photo whatsoever. And these scratches are predominantly trenches in here. So that was, so they brought in high pressure water cannons to spray off to remove the overburden entirely. And this is the water cannon right here being used on Nipissing Hill. And Nipissing Hill is probably about, 110 years ago, something like that. And it's still pretty bare to this day. So removed a lot of burden flush Cobalt Lake. It was originally apparently a clear lake anymore, but that's where a lot of the overburden went. This is an aerial tramway where they were moving high-grade mineralization to one of the mills up on the hill here. And this is Cobalt Lake, right in downtown. So I think this might be Nipissing right here, looking out towards Highway 11 here. I think the train station would sit a little bit off this photo in this area, drain to the bottom of this from ends at depth. Now, as far as the intensification of development goes, this is now we're getting on to the Kuya silver property. So this is known as Jacob's Mine, and Ben went through and researched this. Turns out that's the original Kerr Lake mine, and it was then developed later on. But this is it, probably in what, about 1905, give or take? Yeah. This photograph would have been the area, give or take, and especially with the horse-drawn cart, probably about 2 years later. And so you've gone from literally just a small prospect to major piles of mine rock that have been brought up to surface here. And the interesting thing is that this isn't just one mine. I think the Kerr Lake mine sits right here. This is the Crown Reserve mine here. And I think that's Silverleaf right there. So even just within one photo, you've got 3 mines. Now, Kerr Lake, this is the general outline of it right here. There's a road that comes down right through here, and you can see it. And I think where that photograph is taken in the bottom left would have been taken about right here, facing this area here. That road's still there. We actually used it as drill access here earlier on this late last year. But it comes around here, follows the shoreline, and then goes into the indent. Well, the reason it goes into the indent is because the lake's been drained. That's actually the lake bottom right there. Now, there's these black marks right in through here. And I had a presentation of this back with Laurentian University here earlier on this afternoon. And I asked them what they thought they were, and no one said anything. They're open cuts. So that's where the miners would have gone in, and they would be probably about 2, maybe 3 meters wide at the most, so 5 to 10 feet across. And they're basically like 30 to 40 feet deep or more, where the miners went in just following the vein. So, and then right in here, you can see there's muck rock piles right here. I think more of them right here. We've actually got a mill site right here, a non-functioning mill right here. But on this map here, the Silverleaf property would be about right here, and it extended around the lake shore in this area. And that's one mine. It produced about 500,000 ounces of silver. Crown Reserve starts about right here, goes over through to here. And if you've heard of the Silver Sidewalk, that's on the Crown Reserve. Oh, no, sorry, that's Lawson, isn't it? So that follows this area here. It produced about 20 million ounces of silver. The Kerr Lake mine site starts here and goes over to about here and back around. It produced almost 30 million ounces of silver. The Drummond mine sits right over here. I think it produced about 4 million ounces of silver, 4 or 5. And it would extend from about here up through this area here. And then you've got the Hargrave mine, which is set a little bit south of this photograph here. It produced about another 500,000 ounces. And then Lawson over here, and that is where the silver sidewalk is included. And it produced conservatively about 4 million ounces silver. And this lake, you can drive across it in about 2 minutes. So it's very, very, very highly concentrated silver. This sample here is one that actually Ben found here 3 years ago, I guess, 2, 3 years ago.
Yeah.
Found it somewhere in the cobalt camp. He's never going to tell us where. But you can see the streaks of silver cutting through it. And this is the vein margin right here and right through here. And the majority of this mass of metals is cobalt, but this high grade silver is this right here. And ballpark estimate, this would be on the order of about 5,000 ounce per ton. Okay. Production stats on the camp. We've got fairly reliable data, or at least continuous data, from about 1904 through to 1968. There's a major publication called Sergiades in 1968 done by the Ontario government that went through and documented production year by year for the area. In blue is silver, in red is cobalt, and in green is the nickel production. But 1904 would be about right here. So that's when it was first discovered. And the silver production skyrocketed to 1911 here, and then started to drop off. But what I find really interesting about this graph is that in red is the cobalt, it actually decreases. And I think one or two things is happening. Either the miners were going straight for the high grade silver heart, or they were dumping the cobalt, one of the two. And where they dump the cobalt would be in the tailings pond, so it would have been still there. Agnico Eagle, as far as I know, has gone through and reprocessed a lot of their tailings ponds and probably extracted a lot of that. But that's where that cobalt would have been dumped. And then right through the Depression, production started to decrease. But as far as I'm aware, the price of silver was going down too. So that definitely wasn't helping. A bit of a resurgence post World War II, and then it sort of tapered off and died off. Now, with Kuya Silver, I'd love to see us come back to the glory days of cobalt. Whether it's feasible or not, I would say is probably unlikely. Not impossible, but unlikely. But if we can come back to sort of like production, 5, 10 million ounces, something like that, we'd be very, very happy with that. Pardon me. This slide here talks about the silver production of individual mines. So I've got properties broken out here with the individual production of each, and broken out based on hectares and silver ounce produced per hectare. And again, like it's very much a very tightly distributed camp. The best mine based on the ounces of silver per hectare is actually Crown Reserve, which is one of our major mines. And it produced 20.3 million ounces of silver within just over 9 hectares. So about 2.2 million ounces silver per hectare. And a hectare is what, 100 meters by 100 meters. I put in some of our other properties that are sort of early stage exploration, or I guess at this point, advanced to intermediate stage exploration with no production, and the size then as well. But taking one here just as an example, the Buffalo mine produced 14.2 million ounces on 16.5 hectares for just under 900,000 ounces per hectare. When I gave this presentation earlier on this afternoon, it was actually in the Willett Green Miller Center at Laurentian University. And I find that quite interesting and kind of fitting because Willett Green Miller got his name mapping the rock units in cobalt. So this is his map, initially mapped in 1905. And what it shows here is in green, the Precambrian rocks. So these are the basal Archean Abitibi subprovince that anyone working in Northern Ontario is quite familiar with, especially in gold exploration. Forming these sort of restricted holes, I guess, and I'll call them that deliberately just for a sec. Another one right over here, and then a central granitoid intrusion here, most likely Archean. The Temiskaming sedimentary rocks and the interflow sedimentary rocks that are going to be talked about a little bit more in the talk, he didn't define at this point, but he did define the grade unconformity, which is the contact between the Archean and the Proterozoic rock units. And then the Proterozoic rock units here within this talk, I call them the Huronian supergroup. In some other places in the talk, it's the Cobalt series. but they're all the same thing, or the Huronian supergroup. But it's these buff to tan colored rock units here, and you're dealing with contact between relatively steeply dipping Archean stratigraphy overlain by flatline Proterozoic stratigraphy. It's broken out into the Coleman Formation and the Lorraine Formation. The one that was predominantly the productive horizon in the cobalt camp is the Coleman Formation, and it's this unit in this sort of chocolate brown here. There's actually a second unconformity at cobalt, and it's the contact between the Proterozoic and the Phanerozoic. You've got fairly flatline limestones up on the top of some of the hills, probably part of the Phanerozoic rocks from sort of the southern Ontario area. Yeah. Now the veins themselves, this is where they sit on a map view or on plan view, but this is a section right through that map. And so I'm going from A to B here on this section. And the three rock units that are important, we've talked about the Archean volcanics, and from here on in, it should be noted they're not homogeneous volcanic rocks at all. They're actually volcano-sedimentary rocks, so you've got sediments mixed up with them as well, and overlain by these flatline Huronian supergroup sediments. But the whole thing has been intruded by a Proterozoic intrusion. Here I've got it in orange. It's termed the Nipissing diabase sill. And it's a flat line intrusion that sort of bends and weaves its way through the cobalt cap. Now, you'd think with sort of this gabbroic intrusion that it should follow the unconformable contact, and that would make some sense. Turns out it doesn't. It actually undulates. So in some areas, it's above the great unconformity. In others, it's actually below it. And it sort of undulates back and forth in these areas. Now, as far as it goes with the vein formation or the vein development, the best spot to be is when you're sandwiched between the Archean basement and the Nipissing diabase sill. That's the best historic productive zone. So the entire town of Cobalt actually sits in sort of a little wedge of these Huronian supergroup rocks, and the Nipissing diabase sill here shown is actually eroded out, and it's eroded out from the surface. So you're seeing the rocks beneath it. Kerr Lake is also a small little window underneath the Nipissing diabase sill, but there's areas where the entire sill is still preserved, and just the overlying rocks, like at Colonial and King Edward on this map, this point right here, and then what's called the New Lake Basin, which is this area right in here. And part of the reason I bring that up too is that these veins commonly cluster within these domes and basins. In fact, that was the original interpretation in the cap, is look for the Nipissing diabase contact and then start looking for domes and basins. And I will say that in general terms, the veins themselves, they're restricted to about 75 meters, either above or below the sill. When you get beyond that margin, they start to taper off and die off. So some characteristics on the veins. And here's a photo of a nice vein slab from the Temiskaming mine. This is actually the Kerr Lake vein. I'm not sure if it's silver sidewalk or not, but shown to be about 10 or 12 inches wide and running about 90% estimated silver. The veins themselves, they're generally steeply dipping carbonate veins that typically persist for up to about 200 meters along strike. They've got variable concentrations of silver, arsenic, cobalt, nickel, bismuth. We've also found through the drilling that we've done, they also contain locally copper, lead, and zinc. But the interesting thing is they don't always need to be mineralized. They will taper off into barren veins, and then the mineralization can actually increase again along strike. They do occur within the Archean, Huronian, and the diabase rocks. By far and away, the best host historically is the Huronian supergroup sedimentary rocks. We're also finding the Archean rocks can be a good host as well. In general terms, veins that are hosted in the diabase are not major producers, and that's not to say there aren't exceptions. There are, but in cobalt, it's more the exception rather than the rule that diabase veins are good producers. They commonly occur within arches and troughs in the Great Unconformity. They commonly occur within arches and troughs in the Nipissing diabase. And they've got preferred orientations, and they commonly cluster. So, of course, being a historic mining camp, it's full of rhetoric, suspicions, hearsay. There's other terms that could be used here as well. But there's various thoughts on vein distribution. And in this section here, the columns that I've got written up in red, I would say from the work that we've done here so far, these are the most important. So we need to be within proximity to basal, and I mean Archean interflow sedimentary rocks. That seems to be quite important. Magnetic zones, either highs or lows, or more specifically, right on the contact between the highs and lows seem to be good areas. The lower Nipissing diabase contact may be the better host, but of course, saying that, our data is a little bit skewed because a lot of the main cobalt cap diabase has been eroded out. Jogs or rolls in the Nipissing diabase, including subhorizontal arches and troughs, make good hosts. And the veins are commonly fault hosted, possibly with patchy or sporadic mineralization. Now, in contrast to a bunch of my peers, I'm not necessarily a fan of the spotted chloride alteration, which is fairly well known in the cobalt cap. That's not to say that I don't necessarily think it's important. I just don't think that it needs to be there for a major economic deposit. I've been told that circular fractures in the diabase make for good hosts. I haven't seen any evidence one way or the other with this. Mud seams or underground water flow may or may not be related. Most economic veins restricted to the Huronian supergroup. I disagree on that entirely. The veins are potentially surrounded by disseminated sulfide minerals, namely chalcopyrite, kaolin, and sphalerite, which of course brings up the idea of geophysics. Maybe, but maybe not. That the veins are associated with paleo valleys or depositional valleys of the Huronian supergroup. I'll get to that in just a sec. And topographic highs or lows again. So the initial vein genetic model, and this is back from Willett Green and his protege Cyril Knight back in sort of 1905 through to about 1925. They may not have had all the answers for the vein formation, but they certainly started thinking about it. I just want to read out a quote here from Cyril Knight that was written up in one of his publications. And by the way, the cobalt series is just the Huronian supergroup sediments. The cobalt series is indeed sandwiched between two great igneous masses, which differ from it entirely in character. If we imagine then the three groups of rocks subjected to certain stresses, it does not seem unlikely that the more brittle group, the cobalt series, should develop more fractures than the tougher Keewatin and Nipissing diabase. And that quote is from 1922. So this photograph on the right-hand side was taken by Willett Green, Willett Green Miller, but it shows a vein stepping over and stepping over within this sort of bedded sedimentary rock right here, which I would argue is a bit of an arch here. And he made a very, very clear point that he would have expected that at those breaking points, the vein would have been brecciated, and it wasn't. This photograph, I think, was taken by Cyril Knight. It's in the main, or one of the main stopes of the Cobalt Lake Fault, which is a major fault cut in through Cobalt Lake. And this stope produced about 500,000 ounces silver. And he's making it very, very clear that it is a thrust fault or a reverse fault. You can even see the siliconlides or the scratch marks on the fault face itself. And he made a point that it's a reverse type fault with a displacement of about 550 feet. So not huge displacement, but nonetheless. Subsequent vein genetic models, this started to pick up sort of in the 1960s, pretty much with the resurgence, the post-World War II resurgence in silver exploration. But it was the introduction of the Paleo Valley concept. And what I mean by that is that the Huronian supergroup sedimentary rocks were deposited into, pre-existing valleys. So if you picture the Archean shield at that point, it wasn't a flat plain like the prairies are today. It was more sort of rolling hills. And the idea was that these sort of lenticular valleys right here would have been channelized deposits or river valleys, if you want to call them that here. And that was how they explained that. And then they started looking at the diabase, which is clearly related to the veins, and I don't disprove that whatsoever. But they thought that it was related to magmatic upwelling. And then these sort of these domal type structures and then various troughs would have been thought to be sort of magmatic upwelling. So this would have been a point source of magma upwelling. So I want to point out that even as late as 2015, this idea was still being sort of propagated within the camp. So it's not that this idea has really died out. It's more just this is sort of either people haven't really developed new models, or it's just a continuation of the old models. But here's a schematic of the diabase sill being emplaced, with fluids being expelled off the diabase, forming the veins, and now you've got the diabase eroded out and just the veins left over. Okay. Some early authors started questioning the Paleo Valley vein model as early as 1970. But the idea was still in place even as late as in 2016, 2017, when I first got involved in the camp. Okay, so from here on in, we've covered off on sort of the historical context of the veins. And now from here on in, this is going to be strictly originally first cobalt data, but now Kuya Silver Corp data that we're talking about here. So the data that we've got here is from 2017, and it's still being collected and developed here now. But within that sort of span of I guess 7 years here now, we've done on the order of about 2,200 map points with about 4,000 measurements on everything from Archean bedding, Proterozoic bedding, foliations, faults, veins, etc. We've got 4 detailed and 8 project scale maps of the area showing our models, kinematic analysis of in situ veins, fault systems, folds, mineralized veins. We've also done, pardon me, 2 in situ portable XRF studies of the mineralization of the veins themselves in place. On the order of close to 300 drill holes now, with 40,000 plus meters of drilling. The work done by First Cobalt back in 2017 and 2018 was primarily focused on very much brownfields or continuation of mine mineralization, whereas the work that we've done a bit of that, but we're trying to get more into the brown fields, or even better yet, the green fields. Most of this, we've got oriented core, so we're able to get the vein orientation from this data, and we've got 30,000 or more geochemical assays. These are all up to date, NI 43-101 compliant, that were either full digest 4-acid or sodium peroxide fusion with full QA/QC. We've done a few geophysical and remote sensing surveys of the property, including a property scale LiDAR. And for those that aren't familiar with LiDAR, I'll get into that in a second, and orthoimagery, as well as various magnetic IP, VTEM, and VLF surveys of the area. And Ben's led the charge on this one. We've done over 1,100 historic compiled drill holes with any data that we can put into it. So what LiDAR is it's a very, very high resolution elevation model, a digital elevation model. If you back up a little bit, you can get planet scale or planet-wide what's called SRTM imagery, which is the Shuttle Radar Topographic Mission developed by NASA. It's nowhere near as detailed, but for the purposes of this is probably the better illustration for it. So on the left-hand side, this is a compilation map by John Eyre in 2006 that covers the cobalt area with rock units, the Lorraine granite right in the center, the cobalt camp up through here, the secondary silver camp, silver center camp right through here, the major waterways, etc. This is that same image superimposed with the SRTM DEM. And then we've gone through and filtered that to take off the peaks and troughs, and we're looking more for the relative change. And you can see these corridors coming through a lot more clearly. So now I'm going to shift to the next slide here and show our interpretation superimposed on the geology. And this is what it would look like here. So it seems that there's faults that are coming up the Montreal River and then swinging around and jogging and merging with a second fault right through here. And that's happening right where the mineralization is coming through. And that's that same imagery now draped with the geology here on the DEM and the filtered DEM here as well. So with this vein or this fault system oriented like this, and a second fault system oriented about like this is reminiscent of what's called SC fabric. And if that's the case, sort of at the outcrop scale, this is a sinistral system here, or a left lateral system that would prefer that terminology. And I would argue right now that the silver veins in cobalt, probably their best analogy is actually orogenic gold. So this schematic here, just to sort of start off the rest of the talk now, with this step over right here and then merge into another fault system. you can get a large pop-up structure, or I would term it more in terms of enhanced compression zone right through here. And sure enough, that's where we're seeing the veins in cobalt. So we're going to take a look here at both Kerr Lake and Silver Center here, starting with Silver Center. So the geology at Silver Center here is there's a central dome of the Archean volcanic rocks that's been uplifted, and there's various faults and veins that come through here. The Keeley mine sits right here. Frontier mine is right here. They're the two major producers in this camp, combined produced almost 20 million ounces. And then secondary mineral occurrences or small scale mines here, here, here. Another one possibly right here. But that's the map view. And then plan view here is looking north, and that would run from here to about here. The Nipissing diabase here is shown in purple, whereas on this section, it's shown in this sort of, I don't know, baby blue, I guess is what it's showing on my screen. So that diabase sill actually dips below Silver Center Camp here. And the Woods vein sits right here in Fault Valley, and it actually passes right through the Nipissing diabase and comes out the other side, and it's potentially economic at depth, but it was never mined for any significant amount. I think of what, a 12 million ounce deposit at Keeley, there was about 300,000 ounces produced at below the diabase. But that's not because the mineralization ran out. It was things like the price of silver dying out, etc. Turns out there's other faults that came through like here and here that haven't really been prospected that much. So two areas that I want to look at, and this is some of the work that Ben was specifically doing. The Haileybury vein and the Keeley #1 vein are really good examples. So this is a drone image here that shows that there's a fault that comes up through here, jogs over a little bit in an anti-clockwise manner, and then continues back on. And now this section of the vein itself, there's virtually no mineralization. In fact, there's virtually no carbonate whatsoever. And yet there's a nice big blowout where it jogs along. And I'm going to guess, like I've seen it up to probably about 6 inches wide, give or take. Reports, and Ben, please correct me if I'm wrong, but I think I've heard up to 100,000 ounces produced from this stope alone. And then same thing here, it just dies right out. So sinistral jog with an extensional jog here in the sinistral fault system. The Keeley #1. We've got mafic volcanic pillowed flows right here. And then this slightly lighter green is actually a volcaniclastic horizon. So you're the contact between sort of two flow horizons. It's been folded back on itself, partially offset, and then it reappears right here. Those are S-shaped folds characteristic of sinistral motion. And it's right here, right at the rock contact between the two of them, where the production came from the Keeley #1 vein as well. So the Keeley mine, so those veins would have been about right here for the Keeley one, and the Haileybury would have been a little bit north of this pointer here. But the Keeley mine itself consists of three major intersecting veins. There's the Woods vein, which runs north-south, and a little bit of a splay called the Watson vein over through here. Then there's the #16 vein, which dips to the south, and the #28 vein, which dips to the north. So the beauty here is you've got three veins with different orientations and potentially slightly different styles of mineralization. These two I would interpret as being converging thrust faults or reverse faults, whereas this one, no, it's more of a transfer fault or a strike slip fault. So this is just a model, and now it's a 3D view showing what these veins look like at depth. I apologize if it's a little bit crude. We do need to rebuild this one a little bit. So now I'm going to start taking away the planes of the veins themselves and just show the assay grades taken from the mine from various levels, I think from 12 levels. Okay, so now in blue, these cold colors here, these are around 1 to 20 ounce per ton silver, whereas the hot colors, these represent up to, I think, 12,000 ounce per ton silver. And there's a very, very distinct plunge like this on the one vein, and a second one like this on the Woods vein right here. So you've got two separate orientations of plunges of mineralization here. Well, three, I guess. And this is very characteristic of what's known as transpression. So where you're dealing with strike slip motion that then changes, it becomes more of a sort of reverse type or a thrust fault type displacement. Okay, I think I froze the presentation. Yeah, apologies on that. Um, So like I said, this is characteristic of transpressional deformation. So this fault, which runs up the Montreal River, splays off here and joins a secondary fault. And you've got a whole series of strike slip through to the reverse faults in the center of this arch with a major push-up structure like this. And the mineralization is generally associated with the second and third order structures, not the major first order structures. Okay, so that's Silver Center. Now I want to move to Kerr Lake. So Kerr Lake itself, I've mentioned it before, but it produced about 60 million ounces silver. And the area is known as the Kerr Lake Arch. And the reason it's called that is because to the north here, this is all Nipissing diabase. To the south, this is all Nipissing diabase. That's shown in orange here, but they actually form a large scale arch and would match up. And what's below the arch has been eroded and is now preserved. But the center of the arch itself exposes underlying Proterozoic Huronium supergroup sedimentary rocks. And then below that is actually a mixed sequence of Archean volcanosedimentary rocks, predominantly volcanics over here and entirely sedimentary rocks over here, but these are both Archean. This slide here is quite interesting because this is actually the spotted chloride alteration, but it's defining a foliation here that's superimposed on these chloride spots in this orientation here like that. So one of the reasons why I'm not quite so sold. Wait a minute. Yeah, sorry. Yep, just realized. This slide up in here shows the spotted chloride alteration here, but it's defining a foliation like this here. And I think that's actually axial planar to this fold structure here at Kerr Lake. So here's a cross section. So before we were looking on plan view, now this is south and north, so you're facing west here. So the diabase arch would come up here like this and then back around like this. And then the sedimentary rocks are very, very thin, but they define an arch and then a trough, or more specifically an anticline and then a syncline under this large scale diabase arch. But what I see as a structural geologist is decoupled folding or disharmonic folding, where the more competent rock unit is folding once and the less competent rock unit is folding twice. So these sedimentary rocks are accommodating more strain than the coarse Nipissing diabase sill. And interestingly enough, a lot of these veins follow either the inflection of the folds or the fold axial traces themselves. Okay. Another thing I want to talk about with Kerr Lake is the basement rocks, like the Archean basement rocks, are not homogeneous whatsoever. And this shows the trace of some of the veins right through here and through here, but not the entire vein itself. This is just the productive zones within these veins, as best we can tell. But in this area, it's predominantly mafic volcanic rock. And then in here, these are these thin Archean interflow sedimentary rocks that cobalt's very well known for. They're sort of graphitic black shale through the area. But I find it very, very interesting that the veins are clearly sort of in the area of these sedimentary rocks, but the production is not generally from the interflow sediments whatsoever. So another suggestion that's probably sort of a structural genesis of the veins. And then moving over to the east, there's a contact right through here where these rocks are actually cut off. And now you've got, as best we can tell, Temiskaming sedimentary rocks here exposed under cover, or at least the unconformity here is exposed undercover and not exposed on surface whatsoever. But the Archean Temiskaming assemblage, and I know there's a few outliers, but it's generally associated with tectonism in the Archean, sort of as a mass debris flow, and quite often associated with major faults. So hints that this is sort of an area that's seen several generations of deformation. And sorry, one other thing I wanted to just point out with the previous slide is that this is the bedding orientation in the Archean, in the conformable Archean right here. But these are trend lines for bedding in the Temiskaming assemblage. So two completely different orientations here. Okay. Now, within the cobalt cap itself, we've gone through and mapped out a foliation, and it's generally running east-southeast, west-northwest. This is a pole to the plane stereo net showing that foliation. But we can trace it in the Archean volcanic rocks, in the Huronian supergroup sedimentary rocks, and in the Nipissing diabase itself. And this foliation has never been documented in cobalt before whatsoever. A close-up of the Kerr Lake area, and this is it right through here. There's some Archean foliations here that clearly aren't related to it, but we can almost see the trend line of it in our LiDAR scan, which is this here. This is the elevation contours using LiDAR. And again, I'd point out that first cobalt, we were the first to document this foliation. Now, as far as the veins themselves, there are preferred orientations to these veins, and approximately 80% of the veins correspond with the orientation of Archean bedding. And so I'm not sure how well it's showing up at the back there, but we've got bedding measurements here, and this is defined largely by other people's mapping, not our own or compilation. But trend lines sort of matched up would be about like this here. And a lot of these veins are following that same orientation. So even though the graphitic shales, they may not be the best host for mineralization, they're certainly influential in terms of the vein genesis. And so taking these two slides in concert, if we've got foliation trending about like this, that implies that we've got shortening in this direction. Now, if we've got shortening in this direction, that means that we could have dilation perpendicular to it. And the orientation of Archean bedding here is pretty much parallel to the shortening direction. Therefore, you can basically take a rock bed, pop it open. So I think that's got a lot to do with the vein orientation. What about the role of the Nipissing diabase sill? I've said several times here now that it's obviously crucial to the cobalt cap. And as far as it goes, if you start taking a competent rock unit and flexing it, you're going to start forming fractures in it. You know, it's the case of pick up a piece of wood or a piece of metal bar and start bending and start shattering it. You're going to get shatters right in sort of the inflection point on that metal bar, but only on one side of it. And that's what's being shown here. And this would be a sort of representation of the fracture pattern itself. So this would be probably the other 20% orientation of the veins, is that they'd be following that foliation as sort of axial planar fractures, I guess, but related to the diabase. Now, what about our LiDAR survey? Are there any faults in the area that maybe we should follow up on? And it turns out that yes, there are, and we can see them in the LiDAR and we can see them in the geology. The Cobalt Lake fault runs right through this valley, which corresponds with this valley right through here. We know it's a reverse fault because we've got documented offset along the unconformity itself. But we can see various lineaments picking up in the LiDAR in through here. And I would point out very, very clearly that it's also influencing the Nipissing diabase sill. So we've got pretty clear evidence that yes, there is deformation that affects the Nipissing diabase sill. Okay, so what do we have here? We've got a fairly complex fault pattern. And there's areas sort of away from the sill where the faulting starts to die out. And there's areas like this little wedge right here, right next to the Lorraine granite, where the faulting intensifies. So you're probably getting another rheological contrast with the Lorraine granite. It's probably acting as a very, very rigid body. The Nipissing diabase is behaving as a semi-rigid body, and the volcanic and sedimentary rocks are behaving as relatively incompetent bodies that are accommodating strain. But I find that very, very interesting because now we can start relating the structural genesis of these veins back to Lorraine granite, which has basically never been proposed in the history of the camp whatsoever. Now, why am I so interested in reverse faults? If we've got a transfer fault or a strike slip fault that shifts into a reverse fault or a thrust fault right here, what's the relevance to veining? And the relevance is this: if you've got two blocks sliding one against the other, it requires a lot less applied stress to offset these blocks. But if you turn around and uplift one of these blocks relative to the other, it takes a lot more applied stress to do that. And so the rocks are therefore going to become more strained in that area. And to me, that's the big key and the takeaway right here, is if you can start identifying reverse faults or thrust faults that are related to veining in the area, you're probably in an area with enhanced potential for veining. So I guess if you want to consider it this way, the stress itself is being controlled by the granitoid. If you picture that as an island in a stream, and you've got sort of water flow, and this would be, you've got to picture this almost in reverse, but where that island is, if you thin down your channel, you're going to increase the water flow. And then around the back eddy or the back behind that island, you're going to slow the water right down. And I'd say it's the same analogy, except for in reverse. In this area, we're actually getting increased water flow or increased strain and deformation as opposed to here. So we can probably define two wedges based on that shortening direction, one to the northwest and one to the southeast. And interestingly enough, there's the cobalt silver cap. Here's the silver center silver cap. So just sort of as a wrap up here for the genetic model here, the veins seem to be localized in areas of enhanced compression. I would argue they're transpressional zones defined by fold hinges, Rydell faults with conjugate senses of displacement. And the reverse faults or the thrust faults are exceptionally representative of enhanced shortening. They're concentrated near rock contacts. That's because you've got a rheological contrast or a competency contrast with these various rocks. The diabase sill is absolutely crucial to this, but I don't think that's where the mineralization is coming from. But the Archean interflow sediments are also very, very important for this. Intersections are priority targets. So anywhere we've got, for example, a fold structure like this intersected by Archean interflow sediments, these become high priority areas because these are areas where the veins can nucleate and you can develop a cluster of them. And I think that this deformation is being absolutely controlled by the Lorraine granite, just in that sense. So what drivers do I have for this? Well, we're about 20 kilometers at Silver Center away from the Grenville orogeny front, which has this sort of overall trend that matches up very well. You could also argue it's related to the Pinokian and or the Yavapai orogeny. These all post-date the emplacement of the diabase, and they would definitely affect sort of this brittle deformation experience within it. Okay, how else can we test this? We can test it with the plunge mineralization. We've got areas like Silver Center in particular where we can find two different plunges of mineralization on these veins, which is very, very interesting because now we can start building stereo nets. The plunge of mineralization plotted up, defining a great circle. And as it turns out, that great circle matches up very, very well with our great circle average measurement for the foliation measurements in through the area. Now, how we use that is that it's the vein intersection with this great circle that would dictate the plunge. So if we've got a vein that's striking northwest and dip in moderately or steeply to the east, we can expect that the intersection would be about right here, which would correspond to a steep plunge to mineralization. In contrast, if we've got a vein that's striking about east-southeast, west-northwest, and dipping north, the intersection would be about right here. We can expect that we'd deal with a shallow plunge to mineralization. So we tested this concept at our Campbell Crawford area, which is about 700 or 800 meters north of Kerr Lake, right up in this area here, and about 700 meters east of the nearest mine, which is called Nova Scotia. And again, keep in mind that these vein systems commonly persist for about 200 meters, and that's it. So this is definitely sort of in one of these hinterland areas. Right across the lake is another, I think, 28 million ounce deposit called Deerhorn. But this area, what it has going for it is that on surface, it's Nipissing diabase. So this section shows the diabase, and it persists for about 200 meters depth. There were veins that were known on surface with weak mineralization in it, and there was an adit that was drifted along the vein about 35 meters down or about 100 feet down, but they never actually targeted the lower contact of the diabase. So we put 2 drill holes in. The first was hole 7 right here, colored here, and we try to test these veins, which we knew were there, sort of at the midpoint, and then test where the lower diabase contact was, because it wasn't well defined in this area whatsoever, despite the 1,100 historic drill holes that were compiled. And then we backed it up 50 meters and drilled it again with our hole number 8. And hole number 8 hit high-grade silver mineralization. And this is what we intersected in our second drill hole of the program. So we hit up to 74,000 gram per ton silver, which corresponds to 7.4 weight% silver within this section over 30 centimeters. And then another 51,000 gram per ton, again, corresponded to 5.1% silver. But we hit it within a broader mineralized zone. Now, I'm perfectly aware that the drill is basically drilling down the plane of the vein, and that was not intentional whatsoever. If I back up a slide here, we knew the veins on surface were dipping to the south at about 80, 85 degrees, and we tried to drill like this. As best we can tell, they refract at that lower contact, at least in some areas, and that's where we intersected. But regardless, some of the areas that we hit above the vein, there was no vein material. There was just these fractures here that are actually running very high-grade silver as well, up to about 1%. Okay, so a vertical cross section through the area. Now we get to go and redefine it a little bit. We're quite sure that there's a reverse fault here, the Cobalt Lake Fault right here, but there's a linear topographic depression right here that persists right up to this area here, which we're calling the Cyril Lake Fault. Yeah, it's currently an interpreted fault, but if that's the case, it seems that we might have a repeat of this fault structure right here. And I can tell you now with our drilling here that we've done, it's actually not dipping in that direction. If it exists, it's actually dipping in the opposite direction, probably forming sort of a Horst and Graben type structure. But regardless, and so if that's the case, if the veins are largely concentrated around the first reverse fault, we've now got a second one defined here. So basically you'd have a vein corridor right through here, surrounding that first fault, and then possibly a second one right through here. And keeping in mind that Kerr Lake sits right there. So after we drilled it, we trenched these veins off on surface. We exposed them for about, I think, 200 meters long strike for the one and, 100 meters with the second. But then we actually exposed another one here on the other side of this lake here. And we just finished our second drill program in this area here. We drilled just shy of 6,000 meters. The first 12 of 18 holes have been released. And we started stepping out along the structure, and we've now defined, I think, 6 significant veins that we can trace for significant distances below this diabase sill, plus a whole series of secondary veins. And the best one that we've hit in these first 12 drill holes, we're calling the Tom's vein, and it runs about 2,100 grams per ton silver over 40 centimeters, but again, within a wider halo of further mineralization. But where we're finding that these high-grade zones, our first veins are running about like this on surface and about like this, but it's the intersection with the northwest veins. That's where the magic seems to happen. So, yeah, I mean, stay tuned with us because we'll have the other assays out here relatively soon. And I made a note in our first press release that all subsequent drill holes that we drilled had visible silver and or cobalt mineralization. So just to wrap up here, and I'd like to thank you for your attention through the talk. We've got a large property in a historically significant camp that we'd love to see reinvigorated. We've got an experienced technical team that I'd like to see advance onto other projects while developing this project. And we've had very good grassroots success in following these high-grade vein systems through our new structural model. So thank you very much.
$3,000 ounces. How close are you to having the reserves?
The question is 30,000 assays, how close are we to having a resource? You need to understand that the first probably 25,000 of those were with First Cobalt, where they were, following up on high grade mines and then sort of following on and extending those. So those are not exactly helping our cause here right now. But the ones that we've developed here since, like the second phase 2 program within the Campbell Crawford area here, these are ones where we're working towards that.
So how close are you?
I mean, in an ideal sense, the problem is that our average drill hole with First Cobalt would have been probably 125 to 150 meters. The ones we're doing in Campbell Crawford are about 350 to 400 meters on average. So significant more meters that we've got to do. Probably 10 to 12,000 meters that we would need to do to start building up a proper resource. Because when we get these steep drill holes drilled, I mentioned that the diabase sill, you've got about a 75-meter window where you're going to hit the vein mineralization. As soon as you get out of that, it sort of dries up and dies out. So we've only got a limited amount of distance that we can stay within this productive horizon and start to find anything definitive. So it's going to take more drilling rather than less to do it, just because we need to get through all this relatively dead rock.
Have you been able to put a date of mineralization?
I mean, everything that we've seen here so far suggests that the veins were placed in brittle deformation that cross-cuts the Nipissing diabase. And the diabase is what, about 2.2 billion years. So we've got that. I mean, historically, with the magmatic model, it would have been 2.2 billion years for the emplacement of the veins. There's the Pinokian orogeny at what, about 1.8 billion years. There's the Yavapai, which would be, I think, about 1.6. There's the Grenvillian orogeny, about 1.1 billion years. I prefer the first two for the vein emplacement because we're seeing a little bit of reactivation, a little bit of subsequent deformation that postdates the vein emplacement. So my guess would be 1.8 to 1.6 billion, but we haven't substantiated that. Keep in mind, we're an exploration company. Yeah. Yep.
Questions on the chat page before goes.
If I do this, how do I shut it off?
Excellent. Okay. Well, we just got.
I mean, I'm happy to be flattered. Thank you very much.
That's it. You're just being flattered.
We have that feature mineralized scale, right? The things. What is that mineralized? Are we in the order of 10 grams per ton over a meter?
Yeah.
Or what ballpark?
So the question is, within this larger mineralized halo, what degree of mineralization is it? When we pierced our Angus vein, and by the way, we've named all our veins after Cobalt Silver Kings players. So if you're curious where the naming's coming from, that's where it's coming from, and we'll run in and out of them very quickly. In that particular intersection, away from the vein itself, we hit up to 1% silver within these high grade fractures. We've got other areas on surface where you can see, and you can see it on surface. I need to get the slide itself, but we've got a steeply dip in 5-element vein and then shallowly dip in fractures that are coming off of it. We've run metal detectors over it, and they're running high grade silver as well. How far they persist, I'm not entirely sure. That's something we're still working on here right now. But, I mean, when we drilled the Tom's vein there with that intersection we had in this last press release on Thursday, we were hitting, I think, just about 300 grams per ton silver within this wider halo. So it's nowhere near as high as some of the other veins that we're hitting, but it's not insignificant either. And the other thing is, if we go into production at Campbell Crawford, now we've got a wider mineralized halo as opposed to just the vein, which is, I mean, it's sort of like anywhere from that thick to up to about that thick. in general terms. I mean, we've seen records up to about a 4 foot wide vein, but we haven't drilled anything to that depth or to that level yet.
So just a lot. Keeping our developing these things, how much with this halo contributes to the actual economics?
It probably wouldn't necessarily contribute much to the overall economics of the deposit per se, but it might cover, for example, the mining costs. And if we can have a situation like that, we're in very good shape. Yeah.
Have you noticed any zonation of the minerals? These are multi-level veins. It's not just.
Yep.
Is there a zonation between the cobalt and cobalt?
The question is there any metal zonation with the veins? We've absolutely seen that. There's no question whatsoever. We went underground at one of the adits called the Professor Adit, which is open. I mean, we went in with a handheld XRF and we analyzed on 2 meter centers right through the entire mineralized vein system. And we were able to see sort of a high grade silver core rimmed by cobalt nickel, rimmed by cobalt, rimmed by base metals, rimmed by carbonate material, and repeated. So we can absolutely turn around, use that with our assays from this drill program and try and tune our program for follow-up work.
Is it with your findings then? So narrows you get that.
Possibly. With the I've done a lot of silver equivalent calculations, just more for just so that we can present one number as opposed to several. We've specifically only restricted that to the silver and the cobalt because these are probably the only metals that we're going to be able to recover in economic quantities. Saying that, if we hit high grades, say copper zones, which we've seen either in drill hole or on surface or whatever the case is, when it raises that possibility. And the camp's known for, believe it or not, the highest gross in metal in the camp was the silver, which obviously followed by the cobalt, followed by the arsenic, and then followed by the nickel. So like, and we know that there's economic quantities of nickel, but what about the arsenic? Is that usable? And I don't know. We haven't gone into that level of detail yet, but I would expect in the next couple of years, if we continue developing Campbell Crawford the way that I'd like to see it developed, then we might be in a position to start answering those questions. Yeah.
What's the main
We've got cobaltite, scooterudite, sapphirite, would be the big ones. So they're all cobalt arsenide minerals.
and is there an actual zone that's more problem?
To be honest, we haven't focused on that so much. That's more of a mineralogy question. We're more focused on the structures. So for us, cobalt is cobalt is cobalt. But at the same time, that's something where, a PhD thesis or a master's thesis, or if we can build a business case for that, we could potentially follow up on.
So it's consistent on both sides.
As far as the mineralogy goes, I mean, I'm not going to say as an absolute rule. All the data we've got so far would suggest that, whether it holds absolutely true or not. I wouldn't swear to that. Yeah. Yep.
Yeah. So
No.
the reason I now I
Yep.
and I got into records, which really isn't public information, stuff that they want to destroy and not salvage.
Okay.
And in certain areas, there's quite a lot of gold.
Okay.
And the public isn't aware, and probably you are, that all the refining is done by Iran. And when they sent the report on their payout, they only paid silver and cobalt. They paid nothing else. I found, and I sampled areas, especially around silver fields, where we're running half to 1 ounce of gold. So it would be wise to check some of your areas.
Yeah. The question was related to gold assays on the property. I mean, we've done a few limited, and this is primarily with First Cobalt gold assays. I've heard things like that before. I'm aware of our competitors in Canada Silver Cobalt Works up in the Galganda camp. They're in the presence or in the phase of trying to drill off a gold rich zone. I know that in Galganda, I would be more inclined to do that just because you're near, sort of the major Archean breaks in the camp. But I have heard that about cobalt here on occasion. So the gold was highest where we had Calco. Okay. Yeah.
I'm also saying it's probably high where there's still quarries.
Yeah.
Where you get that cobalt blue with coal, well, then we find receiving with the gold.
Yeah. Yeah. Fair enough. Yeah. Could be. Yeah. I mean, we've done limited testing on that.
You've got to
Yeah.
So you should have seen something. Okay.
We didn't, gold's not one of those elements. Yeah, no. And we've got the pulps. We could theoretically go back and reprocess it.
Yeah.
I know that with the work that we did do with First Cobalt, I think we had up to 1 gram per ton gold in, a couple of samples here or there. Yeah. Yeah, fair enough. Yeah.
Do you have any basic alteration in the host rock?
The question is, do we have any pervasive alteration in the host rock? Let's see if we can go back to this. When we trenched off these veins here on surface, they're hosted within the Nipissing diabase. And the reason I bring it up is because the diabase, it should be relatively homogeneous, should be relatively unaltered, etc. We were seeing vein alteration zones about that wide around the veins. That's about it. I mean, even this photograph right here, that's the vein in Archean volcanics here, and there's virtually no alteration around it. Yeah, so and this again, it's why I have a hard time with this pervasive spotted chloride alteration as a marker for the veins. It might be there and it might not. Yeah.
One slide to show the arch fraction. So the comment was that there's no fraction in the vein. I'm not really surprised. It's it's not in the top.
Yeah.
Floors. When I see no fraction, because I've seen that in sulfates, lots of structure going to wall out.
Yeah.
And then you're trying to trace it, it's totally gone in sulfates.
So the question is to do with the metallogeny of the veins and how they don't seem to be brecciated within the systems. I will say that there's a big difference between sort of the massive sulfide type deposit and some of the cobalt deposits. And the reason I say that is if you're looking at a massive sulfide, you're not necessarily seeing the primary textures per se. You're not seeing the broken chimneys, that type of thing. Whereas in cobalt, you do see that dendritic cobaltite. You do see that sort of that very, very delicate sort of almost leaf-like pattern that shows up. And I haven't really seen that terribly deformed across a lot of these zones. Yep. Anything else?
Can we go back to this slide and figure them out? She might be here. All right,
Dave,
Yes.
traditionally when the miners were mining veins, the structure would always be there, and they could follow the veins.
Yep.
Was there anything that would have given them an indication that they were getting into a blowout where the vein thickened and there was lots of silver?
Yeah. So the question was with miners mining these zones that would commonly change in mineralization, and is there any indication for blowout zones? When we were looking at the professor at it here a couple of years ago, the veins would start to widen. You would start seeing more pink cobalt bloom, the urethriate within the mine system there. On a fresh vein, I'm not sure you'd see that for sure. They commonly did widen up. what else? The orientation started to change a few times. We'd see sort of wobbles in the veins, a little bit of vein anastomos in. Sometimes you'd get more than one vein that would start coming off of a single vein, things like that. But I mean, for us, with the XRF was a way better tool than any of those, because you'd see that sometimes within the system in other areas. And it was where we started getting either arsenic or cobalt or even a bit of nickel coming in with the vein mineralization. That's where that was our best predictor that we were coming into a blowout zone.
I've just got one more question.
Yep.
Can you give us the origin of the word Kuya?
So the question is, with the origin of the word Kuya. I know that we're a Toronto-based company. We've got operations in Peru. I've heard hints that it's either a Spanish derivation. I actually had one student that I was working with that said, no, we've got that in Indonesia as well as a word. But I'm afraid I don't know the origin, Ed. Yes.
First of all, I'd like to thank you for the historical perspective, that especially with all the photographs, it was really interesting. And, you know, you've given us a good indication of the structures that are there and your interpretation of how the instructions affect the mineralization. But I have to ask the question that everybody always asks about cobalt. If it wasn't related to the Nipissing diabase, and you're suggesting the structures were related to orogenies in the 400 million years after the Nipissing, where did the ore mineralization come from?
Yep. So the question is to do with ultimately with the ore mineralization and the source for it, if it's not a magmatic source for the metals. What we have seen, Ruth, is the Archean interflow sediments. They're elevated quite commonly, and we're seeing this sort of a background elevation in copper, lead, and zinc. We've drilled enough that we've seen that there's sometimes zones of elevated cobalt and arsenic within it as well. Sometimes silver. The problem is that one of these areas in particular that I'm thinking of, we also intersected a vein sort of within that zone. So there's that. Is it real, or is it to do with the vein? But I would suggest that I think Louise Rush's thesis was pointing towards nodular cobalt within these sedimentary rocks, within these anoxic sedimentary rocks. It's the best source that I can give. Where the arsenic comes from, where the silver comes from, I'm not entirely sure. But the other thing that Louise talked about was that so I'm talking about vein zonation sort of on a small scale or a local scale. Turns out, as best we can tell, that it changes throughout the camp as well. And when you get sort of in areas where you've got Archean interflow sedimentary rocks, it's dominantly a cobalt system. Whereas when you get in areas where it's more just the Archean volcanic rocks, it's more nickel in the system as opposed to the cobalt. So more than likely, there's at least a little bit of scavenging of nickel from the volcanic rocks here as well. But I mean, even texturally speaking, I mean, I can't look you in the eye and say that, we've seen massive alteration within the Nipissing diabase as a metal source, because the reality is that what we've seen is relatively narrow alteration corridors surrounding these veins in the diabase, and the rest of it is not 100% homogeneous, but very close. There's not a lot of fluid migration unless it's sort of a primary magmatic source. But I still have a hard time with that, and it's because the veins are occurring in brittle structures within the diabase. So, you're either dealing with a case where the diabase is only partially solidified, or where it's cold and hard and no fluids are being expelled. So I'm afraid that's the best I can give. But I'm not necessarily in favor of a large, buried reservoir of extremely high grade silver, 200 or 2 kilometers down or anything like that. We haven't seen any evidence for that. Best we can tell, it's primarily from the Archean interflow sediments. The other thing that I've actually fought Ben tooth and nail on here for years, and I've got to stand corrected in this, is for the longest time, I didn't think there were any Archean interflow sediments in Keeley Frontier in the Silver Center area. And I've got to say that, yeah, there are. We uncovered some in our trenching program sort of late last year. There are Archean sediments at Silver Center as well.
Thank you again for the talk.
Yep.
Appreciate it. I just want to remind everyone that we do have a box for suggestions. If there's a company commodity you want to hear on, please put it in there and I'll do my best to make that happen. So thank you again for joining, and we'll see you guys next month.